Leaf springs may look like simple curved strips of steel stacked together. But behind that simplicity lies an incredible engineering process. Every time you step into a truck, bus, or even a heavy-duty off-road vehicle, you are relying on a part you may never see. But without it, the ride would be rough, unstable, and unsafe. This hidden hero is the leaf spring, one of the oldest and most reliable suspension components in automotive history. From raw steel billets to heat-treated, precision-curved springs capable of carrying tons of weight, the journey is nothing short of mind-blowing. Today, we'll step inside a supergiant leaf spring factory, where millions of these suspension parts are produced each year for vehicles around the world. We'll uncover how steel is transformed step by step into the springs that keep our vehicles rolling safely and smoothly. Before we get started, don't forget to like, subscribe, and hit the bell icon so you won't miss any of our deep dives into the fascinating world of industrial production. The history of leaf springs goes back hundreds of years. They were used in horse-drawn carriages in the 18th century and became standard in early automobiles. Even today, despite advancements in technology, the leaf spring remains unmatched for certain heavy-duty applications. But how do you take raw steel and turn it into this iconic, powerful part? The answer lies in a carefully designed manufacturing process that combines metallurgy, heat treatment, and precision engineering. It all starts with alloy steel, a special kind of steel enriched with elements like silicon, manganese, and chromium. These alloys increase strength, toughness, and fatigue resistance, which are essential for springs that will flex thousands of times without breaking. The steel usually arrives at the factory in the form of long billets or flat bars, several meters in length. Each bar is carefully inspected for surface defects, cracks, or impurities. Quality control at this stage is vital, because any weakness in the material could result in spring failure later. Once approved, the steel bars are cut into precise lengths, depending on the size of the leaf spring being manufactured. For heavy trucks, a single spring can be up to 1.5 meters long, while smaller vehicles use shorter sizes. From here, the transformation begins. Steel is incredibly strong at room temperature, so to shape it, factories use furnaces that heat bars to over 1,000 degrees Celsius, 1,008 degrees Fahrenheit. Inside the furnace, the steel glows a bright orange red, reaching the perfect temperature for forging. Once heated, the steel bars are moved to powerful forging presses and rolling mills. These machines bend and flatten the steel into the familiar curved profile of a leaf spring. For multi-leaf springs, thinner strips are produced and stacked later in the process. The curvature, or camber, is critical. Too much curve, and the spring becomes stiff. Too little, and it can't support enough weight. Precision dies and hydraulic presses ensure every piece has the exact shape needed for its intended vehicle. For springs with eyes at the ends, the circular loops used to attach the spring to the chassis, hot forging machines roll the edges into perfect rings. These eyes must be incredibly strong, since they bear much of the stress during driving. By the end of this stage, the steel bars have been transformed into recognizable leaf spring shapes, but they're still far from ready. Without further treatment, they would bend permanently or snap under pressure. One of the most fascinating steps in the process is heat treatment. The forged springs are reheated to high temperatures and then rapidly cooled in oil or water baths, a process called quenching. This sudden cooling hardens the steel, giving it the strength to withstand enormous loads. However, quenched steel is also brittle. To restore flexibility, the springs undergo tempering. They are reheated to a lower temperature and held there for several hours. This balances hardness and toughness, ensuring the springs can flex repeatedly without cracking. Some factories also use shot peening, blasting the surface of the spring with tiny steel balls. This creates compressive stress on the surface, dramatically increasing fatigue resistance. It's like giving the spring a protective armor, extending its lifespan by years. At the end of this stage, each spring is incredibly strong, flexible, and ready to take on the brutal forces of the road. While some vehicles use a single leaf spring, most heavy-duty trucks rely on multi-leaf springs. These are stacks of steel strips, each slightly shorter than the one below it, forming a tapered profile. The leaves are carefully assembled in layers, aligned perfectly, and clamped together with a central bolt. Steel clips are added along the sides to hold the stack in place while still allowing the leaves to flex individually. This design spreads loads evenly, reduces stress on any single leaf, and provides both strength and flexibility. It's a simple yet brilliant engineering solution that has stood the test of time. Before leaving the factory, leaf springs undergo several finishing processes. First, they are ground and polished, removing sharp edges or surface imperfections. Next, protective coatings are applied. Factories often use electrostatic painting or powder coating to protect against rust and corrosion. Then comes the most important step: testing. Every batch of leaf springs is subjected to rigorous quality checks. Machines flex the springs thousands of times under simulated loads, measuring how well they maintain their shape and strength. Only those that pass these tests are approved for shipment. Today, millions of leaf springs are produced every year, powering vehicles all over the world. From American trucks hauling freight across highways, to buses carrying passengers in India, to mining equipment in Africa, leaf springs are everywhere. Despite being centuries old in design, they remain one of the most dependable suspension systems. Their simplicity, strength, and low cost make them indispensable in industries where durability matters more than luxury. And it all comes back to the mass production process, a blend of fire, steel, and engineering precision that transforms raw alloy into one of the most vital automotive parts on Earth. It's a reminder that even the simplest looking parts in a vehicle often have the most fascinating stories. Stories of heat, pressure, engineering, and innovation. If you enjoyed this behind-the-scenes look at automotive manufacturing, don't forget to like, subscribe, and hit the notification bell. We have many more stories coming about the amazing machines and factories that keep our modern world moving. Until then, drive safe and stay curious. They're the only part of your car that touches the road. They endure heat, rain, gravel, and thousands of pounds of pressure, all while keeping you safe at 70 miles per hour. But have you ever wondered how a car tire is actually made? It's not just rubber and air. It's a sophisticated blend of chemistry, engineering, and precision machinery. In this video, we're going deep inside the factories where millions of tires are born every year. You'll see how rubber meets steel, heat, and science, until it becomes the round black marvel rolling beneath your feet. Let's start with the basics. Natural rubber. Harvested from rubber trees in Southeast Asia, natural rubber provides the elasticity and flexibility that allows a tire to deform under pressure, then snap back into shape. It's essential for absorbing bumps, smoothing out the ride, and handling the constant flexing that happens as the tire rolls. Made from petroleum byproducts, synthetic rubbers like styrene butadiene rubber and butadiene rubber add durability, resistance to wear, and temperature stability. These rubbers help tires perform under extreme heat, cold, and heavy loads, conditions natural rubber alone couldn't handle. Carbon black. Ever wonder why tires are black? That's carbon black, a fine black powder made from burning hydrocarbons in low oxygen conditions. It's added to the rubber to make it stronger, tougher, and UV resistant, dramatically improving tire lifespan. And fabric tires need to be flexible, but they also need to hold their shape. That's where steel wires and textile fabrics come in. Steel cords give structure and puncture resistance, especially in the tread area. Textile plies, usually made from polyester or nylon, provide shape and reinforcement for the sidewalls and body. Chemical additives. A variety of chemical agents are blended in for fine-tuning. These include sulfur, which makes rubber molecules cross-link during vulcanization, antioxidants and antiozonants, which protect rubber from cracking, processing oils, which improve flexibility and workability. Once all the raw materials are ready, rubbers, carbon black, steel, fabric, and chemicals, it's time to start crafting the actual rubber compound that will become the body of the tire. And it all begins in a machine that looks like a giant steel blender on steroids, the Banbury mixer. Temperatures inside can reach over 150 degrees Celsius, 300 degrees Fahrenheit. At this stage, timing is everything. If the mix runs too hot or too long, the rubber can burn or lose its elasticity. Too cold or too short, and the ingredients won't bond properly. So operators monitor every variable: temperature, torque, pressure, and time, with pinpoint precision. Once the batch is complete, the hot rubber is discharged in thick slabs called strips or cakes. These are then passed through two roll mills, huge horizontal rollers that flatten the compound into wide sheets with uniform thickness. Different formulations are prepared depending on the final function. Some compounds are soft and sticky, for tread grip. Others are dense and airtight, for the inner liner. Some are flexible but strong, for sidewalls and shoulders. Each type of rubber is carefully tagged, stacked, and stored. First up, textile reinforcement. Thin cords made from polyester, nylon, or rayon are sandwiched between rubber sheets in a process called calendering. These layers become the body plies of the tire, adding shape, flexibility, and impact resistance. Then comes the steel. High-tensile steel wires are braided together into wide belts. These belts are coated in brass for better bonding with rubber, then cut at precise angles to control how the tire flexes and grips the road. Steel belts resist punctures, reduce tread deformation, and help maintain stability at high speeds. At the very base, thick steel bead wires are wrapped into loops. These beads are what anchor the tire to the wheel rim and keep it from popping off under pressure. Together, the fabric and steel form an internal skeleton, a kind of reinforced frame that allows tires to be soft on the outside, but unyielding at their core. With all the components ready, rubber sheets, steel belts, textile plies, and bead wires, it's time to assemble the tire. This step is called green tire building, and it's where everything comes together, just not quite finished yet. The process happens on a rotating drum. Layer by layer, the tire is built from the inside out. It starts with the inner liner, a thin, airtight rubber sheet that holds air pressure. Then come the body plies, the flexible fabric layers that give the tire its shape. After that, steel bead wires are added on both edges to grip the rim. Next, sidewalls are applied, forming the tire's outer edge, followed by steel belts, laid flat across the top to reinforce the tread area. Finally, a thick rubber layer, the tread, is placed on top. This is what actually touches the road. Once assembled, the uncured tire, called a green tire, is pressed, stitched, and shaped. It looks like a real tire, but it's still soft and unusable. To become roadworthy, it needs one more thing: heat. The green tire may look finished, but it's still soft, unstable, and unusable. To become a real tire, it needs to go through one final transformation: vulcanization. In this process, the green tire is placed inside a large mold, shaped like the final product. The mold is lined with engraved patterns, which will form the tread and sidewall details. Then, a rubber bladder is inserted into the center of the tire and filled with hot steam or gas. As pressure builds, up to several hundred psi, it forces the tire outward against the mold walls. At the same time, the entire mold is heated to around 107 degrees, 340 degrees Fahrenheit. This activates a chemical process where sulfur cross-links the rubber molecules, making the material harder, more elastic, and permanently bonded. Within about 10 to 15 minutes, the tire emerges fully formed, with tread grooves, branding, and structural strength all locked in. Vulcanization is what makes the tire durable, springy, and able to withstand everything from highway speeds to potholes. Without it, a tire is just a pile of soft layers. Now, it's finally ready for inspection. Before any tire leaves the factory, it must pass a series of strict quality inspections. because safety depends on it. First, trained technicians check each tire by hand, feeling for bumps, bubbles, or defects in the tread and sidewall. Then, high-tech machines step in. X-rays scan for internal flaws. Laser systems check balance, roundness, and uniform thickness. Some tires are randomly selected for destructive testing, inflated until they burst, spun at high speeds, or exposed to extreme temperatures. These tests simulate real-world abuse, highways, heat waves, emergency braking. Only tires that meet every safety and performance standard, inside and out, are approved for use. The rest, rejected and recycled. Because in the world of auto safety, there's no such thing as close enough. Every tire must be perfect. From raw rubber and steel to heat, pressure and precision, every tire is a quiet masterpiece of engineering. It's easy to take them for granted, but without them, your car wouldn't grip the road, take a corner, or keep you safe in the rain. Next time you drive, remember, there's a lot more beneath your wheels than just black rubber. There's science, craftsmanship, and thousands of decisions that all lead to one goal: keeping you moving safely. If you enjoyed this behind-the-scenes look at how auto tires are made, don't forget to subscribe to our channel for more fascinating breakdowns of the things we use every day. Hit the bell so you never miss a new episode. Like this video if you learned something new, and let us know in the comments, what should we explore next? Thanks for watching. See you in the next one. In the quiet skies above America, a shadow moves undetected. It's one of the most advanced aircraft ever built, the B-2 Spirit, better known as the stealth bomber. With a wingspan wider than a football field, yet almost invisible to radar, this aircraft is both a marvel of modern engineering and a symbol of unmatched strategic power. But how is such a legendary machine created? Today, we're going behind the scenes, inside some of the most secure facilities on Earth. We're up to uncover the extraordinary process of designing, building, and testing the B-2 stealth bomber. The story of the B-2 begins in the 1970s, during the Cold War. The United States needed an aircraft capable of penetrating deep into enemy territory, without being detected. Engineers and scientists turned to a revolutionary concept: stealth technology. This meant designing an aircraft that didn't reflect radar waves the way normal planes do. Instead of sharp tails and vertical fins, the B-2 was given a sleek flying wing design, a continuous, smooth surface that scattered radar signals. The design wasn't just futuristic, it was nearly invisible to enemy tracking systems. At Northrop Grumman's top-secret facilities, thousands of hours of computer simulations were run. Engineers tested how different shapes reflected radar. Even the smallest curve could mean the difference between detection and invisibility. By the early 1980s, the concept was ready to leave the drawing board and become a reality. The B-2 isn't made from ordinary aluminum. To achieve stealth, its skin required advanced composite materials. The outer layers use radar-absorbing materials, often referred to as RAM coatings. These special polymers and carbon fiber composites soak up radar waves instead of bouncing them back. Underneath, the main structure uses titanium and high-strength carbon composites. Titanium provides durability and resistance to heat, while composites keep the plane lightweight, essential for long-range missions. Every rivet, every panel, even the paint had to be carefully engineered. A standard glossy finish would reflect radar, so the B-2's matte gray coating helps it blend seamlessly with both sky and ground, depending on altitude.